Okay, this example is about the weights of Allen's hummingbirds. I used to think this was some dude named Allen who had a bunch of hummingbirds. Apparently it's an actual type of hummingbird. There you go. But they're studying them in Arizona. So they go ahead, they have a small sample of them. They have 15 hummingbirds, and the average weight in that sample is 3.15 grams. So they're very, very light. Based on previous studies, we can assume the weights of all Allen's hummingbirds have a normal distribution. That's really, really useful, with a standard deviation of 0.33 grams. So what it's telling me is my population standard deviation is 0.33 grams. So the researcher, they want to estimate the true mean weight of all Allen's hummingbirds, so we're going to make a 90% confidence interval. And so one thing just to also consider, my random variable here is hummingbird weight. And you can be more specific of Allen hummingbird in grams. So getting started, state the problem question. It's going to help us plan out our following moves. So because we want to estimate it, it should give away, hopefully it's an estimation problem, but what is the average or mean weight of all Allen's hummingbirds? So one thing to note is whenever we ask these questions, we're asking them for a population. So we will reference the entire population in our question of interest as well as our parameter of interest. So what is the average weight for all Allen's hummingbirds? That's what we're interested in. And what's really great is if you set this question up right there, that is our parameter of interest. So our parameter of interest in notation, so this is notation, and then I'm going to say what it is in description and context. So it is the average or mean weight of all Allen's hummingbirds. So this is the parameter of interest we're interested in estimating. And for my inventory, so I'm going to go ahead and record what I do know here. So I had a sample of 15 birds. In that sample, the average was 3.15 grams. The standard deviation for the population was 0.33 grams. And I can set up the standard deviation of the sampling distribution of x bar. It's going to be that 0.33 over the square root of 15. I tend to not actually do the rounding here. I like to leave it exact, but I can't write out all those digits on here. This ends up being about 0.852 grams. I'm probably going to leave it in this exact form here. So state my confidence level. That's something I'm going to pull directly from here. So it's 99% confidence interval or confidence level. So I can actually figure out, okay, well the z-star I'm going to use, and that's just from this table that we were using earlier in the notes, 2.576. So whenever I want a 99% confidence interval for a mean, and I know the standard deviation of the population, I'm just going to use z-star as this value. So then checking my conditions, was it a random sample? Unsure. And in reality, a lot of times it won't be. Whenever you're sampling people in particular or animals, especially any sort of wild animal, it's really difficult to select them at random. you have to be aware of all of them. You need like a master list, so it's very difficult. So, might be worth an asterisk at the end. Asterisk at end. So we're still going to make all of our conclusions in terms of the population, but at the end we might have like a disclaimer, note this may not apply to the whole population because we may not have a representative sample. However, do everything as if it is. Is n big enough for the central limit theorem to kick in? So one thing that's useful, so we have a sample of 15. Since we know that the population of hummingbird weights is normal, yes, population is normal. So n equals 15 is big enough. Quite honestly, since we knew the population was normally distributed, any sample size would have been big enough. And then do we know the population standard deviation sigma of x? Yes, so that's at 0.33 grams. So on all counts, we were good with the conditions. So just to put it back here, I'm just going to make it 0.33 over root 15 here. 3.15 grams, technically grams, 2.576. So calculate the confidence interval. So it's going to be x bar plus or minus z star times, well, sigma of x bar. So I'm just going to even replace that with sigma of x over root n. So that's going to be 3.15 plus or minus 2.576 times 0.33 over the square root of 15. Just rounding a little bit here because that part after the plus or minus can go on for a bit. 3.515 plus or minus about 0.219. I end up getting, so remember, it's very careful, you want to put the smaller number on the left and the higher number on the right. It's very, very important. It needs to be the order that we naturally count in. Otherwise, we will jump on it. So, from 2.931 grams, it is important to still include my units, to 3.369 grams. So this is going to be my 99% confidence interval for mu of x, which is the mean weight of all Allen's hummingbirds. So now we have to write that up. Oops. So I'm just going to put it back in here. So 2.391 grams to 3.369 grams. So the 99% confidence interval for the mean what? Oh, mean weight of, and here I need to put my population. So all Allen's hummingbirds is on average estimated to be between 2.391 grams and 3.369 grams with a point estimate. So this is going to be x bar from the sample of 3.15 grams. And absolutely, you could say, hey, disclaimer, not a representative sample. Because in general, if you have a study and they did random sampling, they're going to brag about it. If they did it right, almost always they're going to brag about it. It's when they leave it out, you should assume by default they didn't do it correctly. It's a lot safer to do that. So, not a representative sample, so may not represent all Allen's hummingbirds. Oops. So that's what I mean by including a disclaimer. This write-up should be the same, but you can write a disclaimer at the end saying, hey, it may not actually represent this whole population because of this.